So you can run and people kind of disappear. The faster you go, they start disappearing. And so if you run, you can get out of there very quickly. Not only that, if somebody's pushing you, you're going to be accelerated because you're not going to hit anybody anymore. So there's a force, a faster particle, somebody that just got a head start, like in certain economies, is going to start getting richer. Let's call that the inverse Robin Hood effect. And a runaway is possible. All right, that's why a plasma is different. One, it's a fundamental property of plasmas. Plasma is two. In a neutral gas, is a magnetic field, and I don't care. Essentially, unless it feels too hard, then it starts damaging all sorts of stuff. But particles, they have to rotate around the magnetic field. They can move along it, but they can't really propagate across it. Order 0, I'm saying here. And that's not to scale, of course, because the electron mass is 2,000 times smaller than the proton mass, and so that gyro radius for similar velocities is, of course, much tinier. Okay, but the rotation, but the direction, I think I got it right. So protons move left-handed rule around a magnetic field, and electrons move right-handed rule around the magnetic field. And of course, since they can stream along the field, and if they're going a little bit faster and somebody pushes them along the field, clear there's going to be something which allows tails to develop along the field. But perpendicular to the field, it's going to be much harder to develop tails. So in an isotropic ordinary gas, you get Maxwellians. If you try to do that same thing in a plasma, typically you're going to deform the distribution. You might heat perpendicular to the field, but in the parallel direction, hey, you've got a highway in front of you and you can take off. Of course, that's not going to be stationary because generally, once a particle starts running away and a significant number starts running away, our electromagnetic fields, I can send a wave back and forth. And you're going to get wave-particle interactions that are going to they're going to take the place of collisions in the plasma. Okay, that's my two-slide version of plasma physics for you, okay? And the way I like to tell people that don't know about plasmas is that the fact that because the particles have to follow field lines, if the particles are more important, they actually have to take the field lines with them. So magnetic field lines, the lowest order, must follow charged particles in some sense as well, as they move orthogonally to them. They move together. Therefore, particles follow fields, but fields follow particles. The self-consistent magnetic field provides structure and confinement. Electromagnetic fields destabilize and accelerate. The result is that particles and fields are inextricably intertwined. Say that fast 10 times, and I think it gives you an idea of what it means to be a plasma. Okay, now let's go back to our history. Let's go back a little bit to the 40s. Because in 1942, Hans Alfvén, the only plasma physicist to receive the Nobel Prize, noted that in a magnetized plasma, there's a slow wave. There's a kind of combined electromagnetic hydrodynamic wave is produced, which, so far as I know, has yet attracted no attention. And this is, of course, what you all call the Alfvén wave. Of course, some people don't pay attention, but some do, namely Enrico Fermi. So when Hans Alfvén goes to Chicago and talks to Fermi, he says, aha, that's how cosmic rays arise. You have all these fluctuations going around and particles are going bang, bang against these, and you have ping pong paddles and ping pongs that are moving closer, energize, ping pong paddles that are moving away, decelerate, but it's much easier for particles to bounce against ping pong paddles that are coming together because they have to catch up to the ones that are going away, so it's going to be more probable that they interact with paddles coming together, therefore we get acceleration. It's a 3-page paper that everybody should read for clarity. Enrico Fermi, in my view, is the physicist who wrote more clearly in absolute terms to this day. His papers are all readable. There's never a paper that you say, where's the sleight of hand here? How do you go from this equation to this equation? It's all extremely clear. So I encourage you all to read on the origin of cosmic radiation. It defines Fermi acceleration of order 1 and order 2. Coherent, if the paddles are always moving together, or incoherent. And of course, magnetic fields, because of their nature, were being used to, once the hydrogen bomb was done in the early 50s, it became clear that maybe you could control it. And so people tried to develop geometries in which you could confine plasmas for fusion purposes. Why am I saying all this? What's have to do? Well, because there's a cross connection between what we try to do on the Earth and what the sun does naturally. And for a while, these things were held under a series of conferences called the Sherwood Conferences in the West, and these were essentially secret conferences. The Soviets and the Americans and the American influences, the UK, France, et cetera, they weren't talking to each other about these things. But then Kurchatov, who was the head of the Atomic Institute in Russia, they developed the most reasonable device called the tokamak. It just wasn't going to work. So he started giving seminars saying, you know, guys, we have instabilities. It's not working. And so everything became public, kind of all of a sudden in 1958. 1958 had the first public Sherwood Conference in which Soviet scientists came together with Western science and decided to share the geometry and the knowledge of these things. And of course, one topic that immediately became important was something we've already heard of today, magnetic reconnection. And we'll get to that tomorrow in more detail. But there are geometries. So you all know that a current in a wire produces a magnetic field. You also know that wires that have currents going in the same direction attract each other. Wires that have currents going opposite repel each other. So why is a current sheet unstable? What is it? So first of all, in a plasma, there's no wire, right? So I've got current, which is in my volume, and it's moving around. So suppose I have current like this, and I have current like this, for example, if I separate the polarities on the sun and I have a wind that stretches the magnetic field lines out, I have field lines going this way on one side, going the opposite way on the other side, there has to be a current between them. Let's call that a current sheet. Let's suppose that it's not dynamic. And I have a current like this. How does it stand up? What stops this current? Of course, the repulsive Coulomb collisions are, the Coulomb repulsion is taken care of by the fact that there are electrons and protons, so it neutralizes out. But the magnetic part, it can't, because the current, you can think of that current as made up of two little current density wires. These attract each other. So you have to put something in there to stop them from completely collapsing, right? So what do? You either change the direction of the current to make it force-free. We'll get to that tomorrow. Or you put pressure in there. You make gas particles have pressure, so they don't want to be squeezed together. But there's no guarantee that if you perturb the current a little bit somewhere, it's not going to win out or any of these effects. And in fact, that's what the magnetic reconnection process is. And there are very many geometries in which it occurs. This is like a current sheet in the corona. When you have a kink instability, which is another current-driven instability in a tokamak, the whole column just kind of moves aside, but only a part of it moves aside. The rest of it stays in the same place. And as a result of that, you get a current forming between that, and it's a helicoidal current sheet, and it's probably part of what you see in solar flares going on, and so on. And we now know, in fact, Sirovatsky in the early 70s had the intuition that it had to be a dynamic phenomena. There couldn't be a steady state stationary reconnection. But we in the West and even in the Soviet Union, of course, were influenced by very famous scientists that had made models of it. Let's go back to the history, and we'll pick up on the reconnection problem again tomorrow. So I like to show this slide a lot because it gives you an idea of where we were. This is an outreach book from 1948, right after the Second World War, in Italian, and it has this beautiful plate, and it shows the exploration. So of course, radio astronomy had made huge bursts, and it was very fundamental to identify the various layers of the ionosphere. Then we had direct exploration via balloons, and the V2 that was being developed to try to get into space. And here you see the temperature. So we already know temperature is 21 degrees. You all know that when you're flying on an airplane, 10, 12,000 meters or so, temperature is minus 40. Here it says minus 55. But we already had indications the temperature was going up again. You see plus 38, and then there's this plus 100 degree question mark, plus question mark. And he says minus 273. Because I mean, if it's empty and it's black, it should be absolute zero. So it kind of gives you an idea that there's this, we really didn't know where the Earth was in space. But of course, in the early 50s, Biermann was looking at the comet tails. Biermann is a very interesting physicist, and he's connected to Parker for two reasons. If you ask Germans about the solar wind, They said, oh, it was discovered by Biermann, obviously. And of course, we say Parker, but we'll get to that. But there's an interesting connection because Parker in the 50s was working on the dynamo problem. And this Biermann is the guy who invented the Biermann battery, i.e. how you develop magnetic fields when there is none to start with, using the fact that you can have pressure gradients and density gradients that are not aligned. Okay, anyway, looking at the comet tails, Biermann pointed out that there are two tails. There's one that follows the orbit of the comet, plus the drag and Poynting-Robertson forces and illumination forces, but there's one that goes straight radially outwards. And here you can see it in blue, straight outward. And he used that, saying that's got to be ionized, and that's, again, forbidden radiation from complicated molecules, oxygen and other stuff. And I can estimate the speed by doing some fairly simple calculations of the ionization rate here and how the pickup is going to be by this medium. And so it's got to be 470 kilometers per second. He goes and he visits Chicago, and he tells Parker. Now, this whole story is relevant because in 1957, out of the blue, well, not out of the blue, the US was mucking around trying to get a spacecraft up, but there was too much competition because there was the Navy, there was the Air Force, there was the Army. Each one was trying to develop a space missile on their own. They had this series called Vanguard. The Soviets and the Americans had rushed to Germany to try to capture von Braun. And of course, the Americans had won that race, and they brought von Braun to America, the V2. He's the one who developed the rocket that fortunately never managed to get nuclear weapons. But anyway, and so von Braun was working, but you know, this group of people actually working in Ukraine, Korolev, on their own, not really trusted that much by the Soviet elite, was working on developing a rocket. And in 1957, they send up the Sputnik. Now, when the Sputnik is launched, nothing really happens to the Soviet Union. And this is what the New York Times says. So Soviet fires Earth satellite into space, circling globe at 18,000 miles per hour. The sphere is tracked in 4 crossings over the US. That's Saturday. That's the day after the launch. And of course, it scares people because now the Soviets have a capability that the US doesn't have. And so what does the New York Times do? It does what it always does. It tries to people from getting scared. Military experts have said that satellites have no practical military application in the foreseeable future. Yeah, sure. The real significance, and we here have a program of solar exploration and space weather. The nature of the sun, cosmic radiation, solar radio interference, all this information is of an estimable value for those who are working on the problem of sending missiles and eventually men into the vast reaches of the solar system. As a result of this shock, of course, NASA is formed. Right? There's a committee, NASA is formed, and soon after, there's an American launch. But at the same time, Gene Parker sends out his paper. That's Gene seen at the launch of Solar Probe that was renamed after him. And that's Gene. I befriended Gene in his later years because we had similar interests and similar problems that we were studying. And so Parker, as you can see, he's clearly influenced by Biermann. It starts out, Biermann's suggestion. So he accepts the fact that Biermann really is the one who suggested these things. And he says, how does a hot corona expand? And he does a very simple calculation. And he says, okay, the corona is at 1,000,000 degrees. Well, you can think of it this way. 1,000,000 degrees. All right, what's the thermal speed of an electron? So it's ionized. So what's the thermal speed of an electron at 1,000,000 degrees? Anybody venture to tell me? More or less. Order of magnitude. Thermal speed of an electron at 1,000,000 degrees. No ChatGPT. More. That's a proton at 1,000,000 degrees. 100 kilometers per second. Good guess, but that's for a proton. So now tell me for an electron. How much more? Square root of mass. Square root of 2,000. 40, 41, 42 maybe. 4,000. So you have protons at 100 kilometers per second and electrons at 1,000 kilometers per second. What's going to happen? Escape speed from the sun is 600. What's going to happen? Electrons are going to take off. 1,000 kilometers per second. hey, gravity can't stop me, I'm leaving. But if the electron leaves, the protons can't. It's 600, it's 100, they're going slow, they can't make it. So the electrons start leaving. What happens? Set up an electric field. Can't charge the sun. Electromagnetic force is pretty strong, yeah? But stronger than gravity. You set up an electric field. What's that going to do? It's going to say, electrons, slow down. Protons accelerate. And as a result, you get a solar wind, right? In Parker's view, he does it from the fluid point of view. He defines the pressure of this gas, and he tries to figure out what the thermal conductivity of the gas is and the pressure scale height. So it's a very simple equation to write down. If you had a static atmosphere, you'd have dP by dr, and you can write this in terms of pressure, and you can write the integral of that. And you have essentially a scale height, but you have the temperature times r squared in the denominator of this integral. This you can write on a sheet of paper, on that little square of paper. You guys can write it down by yourselves. But that tells you immediately that if t falls off slower than r to the minus 1, the pressure is going to go to a finite value at infinity. And then he argues, well, this is an ionized gas. Thermal conduction, it's a slightly longer version of my two-slide thing, but I could tell you right off the bat. If you remember what the collision frequency looks like, it's like a cross-section times a velocity. The Coulomb cross-section goes like v to the minus 4 speed. That's why things get smaller as you go faster, because the cross-section falls like v to the minus 4. You multiply times the velocity, it means that the mean free path, the collision frequency goes like v to the minus 3, okay? V to the minus 3 is t to the minus 3 halves. So anything that has to do with resistance goes like t to the minus 3 halves. But thermal conduction goes like 1 over that times v squared. And so that's t to the plus 5 halves. And as a result of that, thermal conduction goes like t to the 5 halves, and t of r goes like r to the minus 2/7. That's less than 1. And so Parker concludes, oh, come forward, sorry. Parker concludes, since we know of no general pressure at infinity which could balance P that way, we conclude that probably it is not possible for the corona, or indeed perhaps the atmosphere of any star, to be in complete hydrostatic equilibrium out to large distances. You always expect to find some continued outward hydrodynamic expansion of gas without the genes escape. You always have a tail of a Maxwellian that's going to escape. Even from the Earth's atmosphere, you would have that, right? But this is bigger than that. This is an actual outflow. And he calculates an outflow, and he gets a few hundred kilometers per second. And of course, you're probably familiar with this diagram. Some of you who've taken a course, I'll show you about that tomorrow. But you have this solution that goes through a sonic point. The solar wind accelerates, it becomes supersonic, and it goes out to infinity. Now, of course, that can't happen to infinity because there's the interstellar medium. So there's some small pressure out there. So there's going to be a wall somewhere. What happens if a supersonic flow hits a wall? You're going to form a shock. So there's going to be some shock, and we'll get to that. Now, before any discussion about whether Chapman or Parker could be right really happened, the Russians kept launching, and they launched a spacecraft to the moon. And it missed. And a person from Michigan that you may know, Tomasz Gombozy, was a part of the instrument on Luna 2, Mechta, as it was known in Russia. It made the first measurements of the solar wind because it missed the moon, so it moved out of the magnetosphere, and they got these results that they could see continuous particles hitting their detector, and so they measured the solar wind. June 58, NASA is born. The Simpson Committee says that they want to do a solar probe to pass inside the orbit of Mercury to study the particles and fields in the vicinity of the sun. Because what's this wind that we're talking about? What are these particles coming from? And in the first really continuous measurement is Mariner 2 that was going to the orbit of Venus, between the Venus and the Earth. And you see the velocity as a function of distance. And you can see that there's a wind somewhere between 400 and 750 kilometers per second. You really get the impression that there may be an oscillation in there. Marcia Neugebauer was part of the team there, and Smith were part of the team. And this is the press conference in 1962, end of 1962, where the solar wind becomes official. The discovery of the solar wind kind of becomes official. Now let's go back and look at the corona. You can see that the corona is actually colder from the electron point of view in the polar regions, coronal holes, and it's very hot in those confined regions. And you see that red thing there? That's a prominence. So you have these active regions and you have these confined loops. Inside there, you have pieces of chromosphere floating in the atmosphere, but those are like the hottest regions on the sun. But these are colder from the electron point of view because these are iron lines. So they're telling you about the electron temperature. All right, important to remember that. So now we have a new problem, of course. We have the solar wind problem. Why is the solar wind accelerated? And we have a coronal heating problem. How is it that over the space of a few hundred kilometers, we have a chromosphere sitting at 6,500, 6,700, 7,000 degrees, 8,000. It's dynamics, really hard to figure out what the temperature is. And then over 200 kilometers, boom, 1,000,000 degrees and above. What's going on there? That's a big problem. And this is a beautiful picture that Steve Kramer put together. It shows that in log of distance from the sun, the temperature profile, temperature minimum. Here we're at the end of the photosphere, chromosphere, transition region. Temperature goes above 1,000,000 degrees, 2,000,000,000. We don't actually know the maximum temperature of the solar corona for the ions. We know that for minor ions, it goes way up, and I'll show you in a second, up to above 100,000,000 degrees. And then, of course, there's some collisions occurring low down here when you move up to 1,000,000 degrees. But once you get above 1,000,000 degrees, collisions, they kind of peter out. Everything is just infinitesimally small. And so you become collisionless. And so the real solar wind is not a collisional medium. So this whole idea about a fluid picture that Parker was pointing out, you might have doubts. And in fact, people did have doubts. And they started saying, you can't do that calculation using that way. But it turns out it's not that bad. Anyway, we've been talking about the corona as though it's a steady state. This is just a proof that it's not. This is Solar Orbiter, and we'll get to Solar Orbiter in a second. But Solar Orbiter is the first spacecraft to take telescopes that observe the sun in various wavelengths and move them closer and further from the sun. So what you're seeing is a spacecraft moving in and moving away from the sun. And on the left, you have a very wide angle coronagraph, so to speak, Proba 2, developed by Belgium. And I would like you to notice a few important things. Well, first of all, that associated with active regions and sunspots, you have a lot of dynamic activity. That's easy. For those of you that are theoreticians like me, it's endless. I could watch this thing for hours and not get bored because every time you see new things. One really cool thing is this stuff here. You see how a very small region of the sun produces these immense arcs that fan out like this. And that's right, because if you think of it now, you have a plasma. Well, if you have a dipole in the void, the magnetic field, you can chart exactly how it expands outwards. But now you have this plasma, and at the plasma, you could actually have a really small region on the sun come out and fill a big geometrical angle in the heliosphere. It doesn't say anywhere that the whole heliosphere has to come from the whole sun. In some sense, it does. But in fact, a lot of the heliosphere that you see at any given one time might be coming from a really small region on the sun. And we now have seen that. This is before SDO. We had SOHO. And we've seen what the corona looks like, solar minimum and solar maximum. We see sunspots disappear, activity almost disappear entirely, but you always have bright points. And those bright points have been used to understand many things about coronal heating as well as the dynamo. And magnetic flux correlates with X-ray flux, coming back to stars. And you can see this. There are scaling laws that show for other stars how that correlates. And you have this luminosity that scales almost as the first power of the magnetic flux. And where does this flux, where does the energy that powers this corona and wind come from? Well, it clearly must come from the magnetic field and from the turbulence in the photosphere. And this is a famous picture from an article from Wedemeyer-Bohm, which tries to introduce a little bit more dynamics. You look at that and you get scared, right? Because, okay, the magnetic field, there's some magnetic field between supergranulation cells, but we know that there's the supergranular magnetic network. So there's a very strong field coming out from the network. And there's waves and oscillations. And of course, acoustic modes will tend to shock. We'll get into that tomorrow. Magnetic waves should make it easier, although there's a whole argument about waves versus current sheets producing the heating of the solar wind. I might be able to get to that tomorrow. Not right now. But again, it's all in this, essentially, if you accept that the scale height is so small that shock waves will form very close So basically, most of the shock waves that form from sound waves, why do sound waves steepen as you move up? The sound waves steepen because the density is going down. The energy flux has to be conserved, and therefore the amplitude has to go up. So the amplitude goes up. A regular sound wave steepens into a shock anyway on its own because, essentially the time that it takes for the wave to, in one dimension, to propagate a quarter wavelength, and then the perturbation will have gone over. So essentially, lambda over u is the time for shock, where u is the amplitude of the wave, is the time for shock. And that's, a few thousand kilometers. So most of the sound stuff is going to shock in the upper chromosphere, close to the transition region. So magnetic waves you need. And if you look at the pointing flux is made up of two pieces. And that's really the heart of the so-called AC-DC debate. And it's two pieces. You can bring energy into the corona from the pointing flux by lifting up magnetic flux. Horizontal field, you lift it up and you bring it into the corona. That's called emerging flux, and that's free energy. Or you can take a field that's anchored in the photosphere and move it. That's that second term there, the photosphere perpendicular. That's the part of the photosphere that moves parallel to the photosphere, scalar B. That inclines the field and produces waves. Well, does it produce waves? Well, it depends on how fast you move compared to the length of the field line. If the field line motion is really slow, it's not really a wave. It's a wave if this is fast enough to produce many wavelengths. If this is really, and how long does it take? Let's do a calculation. Okay, I can tell you offhand. Do you have any idea what the alpha speed in the corona looks like? How big is it? Any idea? Let me tell you, it's probably around 2,000 kilometers per second. Okay, take a magnetic field about between 50 Gauss or so, take a density of 10 to the 9 particles per cubic centimeter, you get something between 1,000 and 2,000 kilometers per second. How big is a loop? A loop can be, anything from 20,000 kilometers or something like that. So you get 20 seconds. What's the typical time scale of the motions? It's probably minutes. So it's really slow. So you can kind of think of these field lines as being dragged around slowly. And that's what kind of Parker said. That said, well, okay, now I take a field line and I drag them slowly. Well, I'm going to drag one here, but the one next door is in a different area of the sun. It's going to be dragged in a different way. So the field's going to produce shear. There's going to be a current between them. And therefore, this current is going to be unstable. It's going to produce tiny little flares. That's how I'm going to heat the corona. But then the wave people said, well, we know it's just these waves. I'm banging around here. And these waves go back and forth and they dissipate. So it's the same source of energy, but it's just a question of which time scale dominates in the energy flux. And then, of course, there's emerging flux, which might be the most important one of them all. Emerging flux, while you can think that you can estimate the wave energy flux fairly simply, the emerging flux is very difficult because you need the horizontal field, which is hard to measure. You can't really measure the horizontal field very simply, and not with the time resolution that you would need to figure out how much is coming up and how fast, right? Okay. So now let's take our simplest corona, but we put a magnetic field in it. And remember, these electrons want to leave. What happens? Well, they drag the field out. Okay. And they drag the field out, so you get this current sheet forming here. And that current sheet has an incredible history. Of course, it was observed by the first spacecraft in situ in the solar wind. And people tried to build equilibrium models of that. And for many, many, many years, people believed that there was this configuration where you had these open field lines, and this thing was kind of stationary. They actually believed you could produce that. And two very famous astronomers, Newman and Kopp, actually produced a solution published in Solar Physics, in which they had a cusp here where the closed field line, the last closed field line, had a cusp in it, and then there was a stagnation point in the flow. Now, interestingly enough, in the history of science, these things happen sometimes. Turns out nobody ever verified that solution. Turns out nobody was able to reconstruct it. And when you went to the source and asked them, it turns out the solution was found by a PhD student. And at the time, the computations were done on computers with paper printouts. The student went off and did something else. He took the paper with him. Newman and Kopp could not reproduce their own solution. Numerical simulations kind of did, but numerical simulations, when I was a kid, when I was your age, highest resolution was like 100 by 100. that means that your Reynolds number, your magnetic Reynolds number, the viscosity in your thing is 100, essentially, or 0.01, to translate it properly. That's huge. The actual viscosity in the solar corona with these temperatures is 10 to the minus 10. So we're talking about orders of magnitude. Now, if you take a very viscous flow, you can stabilize stuff that isn't stable. You know, with a very viscous flow, you don't have turbulence, right? Try making turbulence in peanut butter. It just doesn't work. No matter how hard you shake, you ain't going to get turbulence. You're going to get maybe a vortex. It'll die before your arm breaks. But anyway, so people found that. But as the resolution started going up, things started to change. Some simulations started saying, "Oh, this thing doesn't stop. It just goes burp, burp, burp. It's unstable." And the first people that found that actually were a group that were afraid that it was a problem with their numerics. That's how our mindset. I'm telling you this because we're all scientists, we're aspiring scientists, and we tend to work with confirmation bias, right? So we tend to think that what is established has to be correct. That's not true, especially in plasma physics. In plasma physics, let me just make this grandiose statement. It's like we know the first layer of paint on a statue, but that doesn't tell you what the statue is made of. The minute you scratch, you find stuff that people haven't thought of because it's a highly nonlinear system. And so what we really know is very, very little. And I'll give you some more examples of it. But anyway, so the first people that did this were afraid to publish. And some people started publishing and people started understanding that intrinsic thing that's intrinsically unstable. That region there is very different. It can't be stable. It's got to be dynamic. So now we have the dynamics of the small magnetic fields, but we have this big configuration that even with everything else being completely static and stationary is unstable. So you have another source of dynamics. Of course, now the sun's rotating, so what's going to happen to those fields? They're going to be curled up like that. And the sun is inclined. The rotation axis is inclined with respect, and so you get this mess. Now, the person who drew this, we used to call it the ballerina skirt. I don't like that particularly because I think it's just a wavy, surface or something. But anyway, it's wavy and it's unstable too. So it's really hard to make a drawing of what it should look like. But far enough away, this thing kind of becomes metastable. So if you move away at Earth orbit or longer, this thing becomes fairly thick. And it's, you don't see dynamics going on, strong dynamics going on all the time. Now, we've had one spacecraft, the Ulysses spacecraft, that's gone over the poles of the sun, essentially. And it's done one standard solar cycle, 11 years. So this is in the early 90s. The story, that whole spacecraft has a beautiful story that has to be told another time. Anyway, what did it see? It saw that once you got above about 30 degrees, solar wind at solar minimum was almost steady. I mean, the velocity, this is a polar plot of the speed, and the color is the polarity of the magnetic field. So in 1992, it was outward in the North Pole, inward in the South Pole, but you see there's this continual oscillation. But it's about 750. Mean is about 750 kilometers per second. Okay, let's go back to Parker a minute. Parker says the solar wind at Earth's got to be 400. With 2 million degree corona, it's about 400 kilometers per second to Earth. We're 750 here. It's not okay. It's not enough. Okay. Part two, what drives the Parker solar wind? The electrons. Remember, it's the electrons that escape. It's their pressure that speeds up the wind. But the poles, as I showed you before, is where the electron temperature is coolest. They're colder electrons. They scarcely reach 1 million degrees. It's not even clear whether electron temperature actually gets above 1 million degrees in a coronal hole. So wait a minute. I got slow wind coming from the equator where the electrons are hot, and I got fast wind coming from the poles where the electrons are cold. As something's not standing up here. That's pretty clear. One thing's clear for sure, it's turbulent, because there's an oscillation on top of that 750, which is of order 60, 70 kilometers per second. So the flow is also turbulent. So it's not just a nice steady outflow, it's turbulent. That's a solar minimum. And of course, you've got this mess here at the equator because there's confinement, then it opens up, then it closes, it's open up. And so you've got these slow, fast, oscillating all the time. Solar maximum, hey, anybody care to try to explain that? 11 years later, we went into this really deep minimum. And you may have heard about this very weak minimum that we had. And so the momentum of the solar wind was smaller. The density dropped dramatically, but the speed, incredibly, was pretty much the same, 750. Okay? So there's something about the process which leads to the same asymptotic speeds, even though the cycle is much weaker. Those high-speed streams in the fast solar wind had some very high jets, went all the way up to 820 kilometers. And they were of the same order of magnitude as the Alphen speed, and they were called Alphenic jets at the time by Marcia Neugebauer. And there was this weird thing happening to the magnetic field. Remember the magnetic field, well, this is 2007, so let me go back one. 2007 is we're over here. So the North Pole in 2007 was inward, so the radial field was negative, okay? So let's go forward here. So you see that the average field was negative. But wait a minute, field popped up to positive as well. So in Ulysses, if you looked carefully at these plots, up in that red, there was a little bit of blue. And down in this blue, there was a little bit of red. I was intrigued when I saw that, in fact, and I started working on that problem. But we'll get to, so there's something weird. The turbulence is such, so clearly those are not locations in the coronal hole where the magnetic field is opposite. That wouldn't, the magnetic field is pretty strongly of one polarity. The field that actually gets out is one polarity. So those are field lines that actually kink. So the turbulence is so strong that the field line bends backward and then forward again, all right? So that, we thought that was like a weird thing with Ulysses. It was a strange thing. I'll show you towards the end of this talk what actually happens. A little bit more about the structure of the magnetic field. So I told you the magnetic field can have these confined regions called pseudostreamers and the big streamers. The big streamers are the ones that lead to the heliospheric current sheet further away and to slow wind, these big things here, striations. And people have thought that the currents that are involved in the stretching out of these structures play an important role in accelerating this kind of slower type wind. I'll try to get to that more. But let's go to the contradiction between fast and slow again. I'm just showing you here the speed of the solar wind that you can see here in dashed, and a measure of the electron temperature in the corona, which is obtained by the ratio of ionization states. So what happens is that as long as there are collisions, you can change the ionization state, say of magnesium or oxygen or some other heavy metal. Once you get far enough away, the electrons don't collide anymore. So the composition, that ionization rate is kind of frozen in. Even if you measure it at 3 astronomical units or 4 astronomical units where Ulysses was, that tells you what the electron temperature at the last collision was. And you see this beautiful anti-correlation. So high temperature, low speed, low temperature, high speed. If you look at the minor ions in the fast solar wind, you get oxygen 6 up above 100 million degrees, other ions slightly less, neutral hydrogen somewhere around 2 million maybe, and the electron temperature, it's not very clear whether it actually hits a million or so. So we have this dichotomy at solar minimum between fast and slow wind, okay? And this is at further away, towards the orbit of Earth or so. So you have hot protons in the fast wind, they're colder in the slow wind. You have cold electrons in the fast wind. The electrons, they're subsonic. The solar wind flows at 500 kilometers per second. I was telling you that the thermal speed of the electrons is 2,000 kilometers per second. So the electron thermodynamics is a big, fat mess because the flow is subsonic. It's not clear what wave-particle interactions do. So it's very hard to establish a systematic change in something like the temperature of the electrons. You really have to look at the distribution function, which has got beams in it, it's got a halo, it's got a strahl, and so it's very complicated. But the protons is a little better. So you can see that the protons are kept hot, but the electrons, anything goes between fast and slow. All right. And this is an example of proton distribution functions from the Helios data, which tends to show how in the slow wind you have something that looks more Maxwellian-like, but in the high-speed solar wind, you get these bicycle seat shapes with some kind of energy at higher speeds along the magnetic field, which isn't surprising on the basis of my Albite 2 slide lecture. All right. Fast and slow solar wind origins. I don't want to get into too many details here because I won't, but Wang and Shealy using both SOHO and then the stereo mission, which managed to measure things away from the Sun-Earth line, so it could see things that it would see at a 90-degree angles on the limb, things that we saw only directly, and vice versa. They derived a profile for blobs emitted from the helmet streamer tips, and that kind of follows a Parker-like acceleration profile to slow winds. So there's a contribution to slow wind from this opening and closing of the helmet streamer, for sure. All right, so why did we launch Parker Solar Probe? Parker Solar Probe was launched in part to try to figure out some of these enigmas. You know, how do you get to these high speeds, 750 kilometers per second in the high-speed solar wind? What does the temperature actually do when you get close to the sun? We don't really know. Before Parker, the closest measurements we had made was the Helios spacecraft in Germany, which was basically the orbit of Mercury, 0.3 astronomical units, around 70 solar radii from the sun. So Parker was developed, it used to be called Solar Plus, to get inside what we call the Alphen point, where the solar wind speed becomes smaller than the magnetic speed of the waves, the slower waves that Hans Alfvén had discovered. So this is the reasoning behind trying to get to that distance. And of course, trying to figure out how turbulence, I told you it was turbulent, what the amplitudes would do and whether they could boost the wind. And of course, a parallel mission was launched almost at the same time. It was mostly an ESA mission, but the NASA contribution has a great story that Lika can tell you about if you're interested in what we called saving Solar Orbiter. Lika Gotorkota played a major role in making sure that Solar Orbiter could fly. It had very similar objectives, except that because it's moving out of the ecliptic plane, it also wants to try to understand a little bit more about the flows and the cycle and try to see that high latitude magnetic field, what it does. So as you may know, Parker has completed its main mission phase. We had 3 perihelia and 9.5 solar radii. The last one was in June of this year. And we are now hoping for extended mission, of course. And so this is Solar Orbiter versus Parker. So Parker is in the ecliptic plane, so it can only see plus or minus 7 degrees with respect to the solar equator because of the inclination of the rotation action of the sun. But Orbiter is going to work its way all the way up to 33 degrees, and this is a timeline of that. And so this is now the first perihelion of Parker Solar Probe, and I'm showing you the measurements of magnetic field, radial component, magnetic field magnitude. So the perihelion was at 35 solar radii, okay? 35 solar radii, that's half the orbit of Mercury, okay? So it's 0.15 AU. And we're clearly in a negative polarity region of the sun. But look at what the magnetic field does. This is the radial component. It goes boop, boop, all the time. Remember those oscillations from Ulysses that I was mentioning before? Now it's doing it all the time. At the beginning, people thought maybe these are heliospheric current sheet crosses. We're in the ecliptic. So we maybe just the current sheet flaps so much, we're going back and forth. Nope. Because if one looks at higher energy particles that follow field lines, you can actually see that the fast electrons during those reversals are moving towards the sun. So they're on a field line that's hooked backwards. These things are shooting away much faster than the solar wind along the magnetic field line. When the field line turns, they turn and they go back. Then they come back out again. So these oscillations are happening all the time. Notice that the magnitude of the magnetic field is pretty much constant. These are the strongest fields we'd ever measured inside the solar wind, 100 nanotesla or so at the time. And this is the solar wind speed. We were in really fairly slow solar wind. But do you notice something weird about this plot? Is there anything that captures your imagination on this plot from a standard, average speed plus noise on it? I mean, what would you, let me say this a different way. What would you expect a plot? Suppose I had something that was moving at 500 kilometers per second and it had plus or minus 50 kilometer per second noise on it. What would it look like? Would it look like that or not? Or is there something about that plot that doesn't look quite right? Normally when you see a line, you see noise around it, there's a band, right? But there's no band here. the band only goes up. There's a well-defined lower boundary. What's going on? There's kind of a baseline wind, and there's jets only going one way, up. There was a physicist who noticed this before probe in some data taken at 1 AU. His name was Jack Gosling. Especially in the high-speed solar wind, he'd see these one-sided jets. And he came to me, because we were friends, and said, Marco, what the hell's going on? Why is this thing going up all at once? Well, it turns out I wasn't capable of answering the question, but luckily enough, a student of mine came up with the idea, and I'll tell you about it later. We now understand why it's one-sided, but it turns the whole study of turbulence in the solar wind into a fairly complicated problem. The reason is, you see these reversals here? They happen to be correlated with these jets, 1-to-1. So when the magnetic field, say, this case is pointing downwards, and then it flips at exactly the same time, the solar wind goes from 250 to 350. Then it comes back down to 200. So it looks as kind of one-sided turbulence, if you want. Turbulence that only goes one way in the velocity. The magnetic field, it goes bang, 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 bang. But the velocity just goes up, and it comes back down, up, come back down, up, come back down. So it's not your standard study of a system which has an average and noise. Something different. So it's so different that it doesn't really have a name yet. The average solar wind speed is clearly higher than the baseline. The average solar wind speed is sitting somewhere in the middle of that thing. So it's faster than the baseline. So if you were to dissipate that oscillation, you wouldn't get the baseline. You would get something faster. And I'm going to introduce the name to you. I'm going to call it the Gosling boost because Jack Gosling discovered this a long time ago. All right? And it has to do with the nature of the fluctuations that are propagating the wind. But I can't get into it right now, but I'll get to it later. Let's look at the details of this magnetic field. The magnetic field goes up and down, but the magnitude stays constant. The magnetic field so this is a detail. This is from 7 a.m. to 9 a.m. on 6th of November, 2018. Look at the magnitude of the field. It's sitting at 100 nanotesla. The magnetic field goes up and down, the radial component, but the transverse part oscillates in sync so that the magnitude stays constant. So now we have a magnetic field vector that, okay, if you go far enough away, it increases in magnitude, right? When you get close to the sun, the magnetic field magnitude is bigger. But on the fast scale, it's just a vector moving. It's like a unit vector. It's running around on a sphere. Magnetic field is divergence-free. You have this weird dynamics of a vector of constant magnitude, and it's divergence-free. You can call it turbulence if you like, but it's pretty weird turbulence, right? Because you'd expect the magnitude of the field to go up and down. There should be a delta B over B, which is, the same order of magnitude as the fluctuation, but it's not. The magnitude of the fluctuation is much bigger than the fluctuation of the magnitude. It's essentially incompressible. Remember, if you change the intensity of the magnetic field, that produces a big pressure in MHD. We'll see that tomorrow. This is incompressible. The field is just rotating around in a sphere. So let me give it away. The velocity field is exactly correlated with the magnetic field, with a sense of correlation which depends on the average direction of the field. So if the baseline vector is negative, the field U is perfectly correlated with B. So that when B switches up, U switches up. If the average field is positive, U is anti-correlated. So when B goes negative, turns down, U goes up again. That's why you always see it going up. Because depending on the sign of B, it's either correlated or anti-correlated. Now, we haven't done alpha and waves. We'll do them tomorrow. But if you remember anything about alpha and waves, or if you studied MHD at all, you will know that the wave that Mr. Hans Alfvén discovered had this property. It was transverse. It wasn't spherical. Okay? Just forget about that for a second. But if the field is going one way, and you want the wave to go along the field, then U and B have to be anti-correlated. If the field is going inward, U and B, and the wave goes in the same direction as before, U and B are positively correlated. Let's translate this now to our problem here. We have a magnetic field coming out of the sun. A wave going outward would have U and B negatively correlated. So when B switches back, U switches front. Okay? Now we have a magnetic field coming towards the sun, but we still want an outward wave. An outward wave with a magnetic field towards the sun is positively correlated with the magnetic field. So now we flip the magnetic field, turn a kink in the field line, B switches plus, and U is now positively correlated. It switches plus too. So these are big, fat Alphen waves, humongous Alphen waves that switch the whole field around, but they're all propagating away from the sun. So that's what the solar wind looks like at 35 solar radii. It's dominated by these humongous waves, mavericks, if you like, but they're actually called switchbacks these days, that propagate away from the sun. And they're everywhere. No matter where you are, most of the time, you have these things coming away from the sun. Oh, I should be almost done. Sorry about this plot. This is to scare you. These are all the orbits of solar probe until the next to last, and it's the radial magnetic field. So you see all those things up there with all these switchbacks, the radial oscillations. They're still there a lot of the time. Sometimes they are mysteriously absent, and they reappear a little bit. But most of the orbits we see these. The relative amplitude, as you see as we get closer to the sun, tends to get smaller compared to the mean. See that here? The field here, of course, is up to 2,000 nanotesla, all right? It's 10 times bigger than it was up here. Fluctuations, though, are a little bit smaller than they were here. There's a reason for that. It has to do with the conservation of energy flux. As you move away from the sun, the relative amplitude of the waves grows. And so that's what you're seeing here, is the fact that closer to the sun, the wave amplitude becomes smaller, okay? But we see these things throughout all of the Parker Solar Probe orbits. Now in Parker, you can actually see Parker Solar Probe is the first probe that goes so close to the sun that when it's at perihelion, it rotates faster than the sun. But when it's far away, it rotates slower. That means, if you think of it, that there's a moment in time when it's moving around the sun's rotating in sync. During that time, from the point of view of the sun, the probe's only moving in or out. So it crosses corotation twice. That means that you get a chance to go in and out of the same solar wind stream at different distances from the sun. So when you plot, when you're sitting away at 1 AU and you measure a time series of the solar wind, you can consider that time to be space. With solar probe, you can't, because you're going so fast that you're measuring in longitude rather than in space or time. And so you should plot it like that, with this curve that shows the 3D structure in R and longitude from the point of view of the sun. Let's see if I can get that to work again. Yeah, here. So it rotates around. And if you do that and plot it in 3D, you kind of visually see that maybe this guy and this guy are the same, this guy and this guy are the same, and so on. And you can try to line them up and see how fast the solar wind is accelerating. And clearly we got one wrong, this blue thing here. But the other ones, the fact that those gradients are pretty much the same, give you faith that you've actually recognized the same solar wind at different distances from the sun. And you can start measuring that acceleration. So that's another important thing the solar probe has given us. And by the way, this is consistent with the push given to the wind by the temperature plus the waves. Let me skip over that. If you put all of the plots of the solar wind speed together, you can see that the baseline looks something like this. And if you bring this all the way to 1 AU, you get something that looks pretty much like the Parker solar wind. So there's this kind of lower limit to the solar wind speed that seems to be an electron pressure grid driven solar wind. But the bulk of the solar wind is systematically higher, and most probably it's due to the boost structures and waves and turbulence that are propagating in it. I would say that's most likely. Now, what drives those is the subject of humongous debate right now, whether it's dynamic effects at the sun, reconnection, something like that, or whether it's just oscillations from the solar photosphere penetrating through. It's turbulent. This is demonstrated through spectra. I don't want to go into the details. The spectra, there are magnetic field spectra exist. They have an inertial range with a slope. The slope typically is in the ballpark of what we expect from standard magnetohydrodynamic turbulence. It's anisotropic. The slopes are different in the perpendicular direction to the parallel direction to the field. I don't want to go into this right now. It's not very important. But the slopes are consistent with standard theories of MHD turbulence. So there is an ongoing turbulent evolution of solar wind. And this is what the heliospheric current sheet looks like. Solar probe carries a white light camera on it, which uses the shield as an occulter. And that's what the heliospheric current sheet looks like. Reality. You can see that it's intrinsically dynamic as it's forming, and you see these blob. Oh, you see a CME going off there as well. But if you, again, this is something that needs to be looked at intensively for a long period of time. I'm almost out of time here. We can see magnetic reconnection. Well, I'll get further into that. Let me just briefly, since we've done this whole parkour of the heliosphere, let's get to the end of it. And you guys recognize what that is, I hope, right? What are we seeing here? What's this? Anybody tell me what that is? Sorry? Of course, it's a sink, but I'm asking you. But we're physicists here, right? I'm asking you what this guy is. I'm not asking you whether this is a kitchen sink. It's pretty obvious, this kitchen sink, right? What is it? What's that guy? Why does it do this? What's going on? Don't feel shy. That's not. It's a shock. That's a shock. Why? Because the speed of the water when it hits your kitchen sink compared to the velocity of the surface waves in thin film of water, it's supersonic. You have a supersonic outflow. But of course, that water moves away, and then you have your sink, which is unfortunately made like this. So the water accumulates. And as the water becomes thicker, higher, water accumulates, you have a shock. If you put a finger there, you'll form a bow shock. You can do it. Do this experiment. You can do it in your bathroom tonight if you haven't never done it before. Typically, Now, if you incline your sink, like over there, then you get a beautiful bow shock. There, I've decided that there is an average direction of drag pushing at you. So you can imagine the heliosphere moving into a solar wind or something, an interstellar wind. And then you'll get this beautiful shape here. The other thing, I'm not showing you the movie because it's kind of trivial, but if you let this go and your sink is horizontal, the water accumulates, so that shock moves in because the pressure of your interstellar medium is going up. And so the shock moves in closer and closer to your nozzle, which is our generator of our kitchen sink wind, okay? You don't have any other shocks that you guys can make apart from this one is a very simple shock that you can make. Do you have any other examples of home brewed shocks that you know of? Yeah, how do you make it? Yeah, yes, exactly. The breaking, sorry, he was saying a rope or, of course, a whip. The breaking of a whip is a shock, yeah. Or if you're good enough, that should also be. I think so, yeah. Anyway, so what happens in this case of the sun? So we know there's a termination shock for sure because Voyager crossed it. But what happens at the edge where we end up into the heliosphere? Well, there's some very complex physics going on. There could be a shock or there couldn't, depending on the wave-particle interactions that are occurring. Now, it happens to be that the interstellar medium is a very complex medium thermodynamically. There are a lot of neutrals. There's a lot of radiation. There's a lot of hydrogen. So you can have charge exchange between particles. And charge exchange means that you can load the mass. And all of a sudden, if you increase the mass of the outflow, it slows down. And you can actually end up only have like a thicker wave rather than a shock. And it now seems that that's the case. So there is an internal shock, which is the edge of the heliosphere, which was the first picture that I showed you, essentially almost spherical. And then we have kind of a bow wave circulating around it. There was a mission, IBEX, and soon to be launched IMAP to study the shape of this and to study the energetic neutral atoms coming from interstellar space. All right, this is a blah, blah, but we'll get into it later. And so there's been an observation, of course, of a so-called ribbon, so-called ibex ribbon, which is why do we have an excess of neutral energetic atoms? And this kind of highlights the field, the direction, orientation of the interstellar field with respect to the heliosphere itself. And this is a simulation published in Nature by Merov Ofer. So in fact, the outer part of our heliosphere ends up looking something more like a French croissant of some kind, with a magnetic field coming in at an angle and roping around it. Very recent work. So I'll stop here. I think I'm on time, right? All right, so to be continued. So tomorrow we'll talk more about MHD and turbulence. I'll try to give you the equivalent of a 2-slide version of MHD with MHD waves, physical comprehension, not the details of dispersion relations. No, some features of it, yes. But I want you to remember the features more than anything else. And of course, when you go and then interpret data or want somebody to interpret data for you, it's important to have a grasp and handles of, the basic invariants and things that can happen and that make sense. So, well, that's the point. All right, thanks, and we'll continue tomorrow.
Thanks for the presentation. It was really great. I'm not really a sun person, so this is great. There's a picture, there's a plot with all of the observations from Parker, and the very bottom one, it looks like it's going down. Like there's these but the rest of them are going up.
Well, that depends on the sign of the magnetic field, right? So that's the reason. If the magnetic field is positive, the reversal goes down. Otherwise, it goes up.
Right.
Yes,
Okay.
it's just that we happen to be, most of the perihelia, we happen to be in a negative polarity region of the sun. And then, so make a long story short, the reason I was mentioning the fact that you can have a small funnel, it has to do, it turns out that Parker was connected, and especially in its first perihelion, to really microscopic coronal hole. Oh. It was hugely expanding, and it gave rise to that stuff that you saw at the beginning. So you see, most of the time, for reasons that we, have to do with chance and nature, we were connected to a, go back. I don't know what happened. So there, you just stop there. Yeah. You see, most of the time, we're crossing in negative polarity regions. There's some in the middle there that have the same feature.
Right.
You can see the current sheet crossings. The current sheet crossings, you can see the magnetic field like a staircase coming down, and you can distinguish them very well from these other things that are the switchbacks. Yeah, yeah. That's going to be, that's an endless set of data for machine learning, AI. All the stuff that you guys are going to talk about. I think there's so much stuff in there. We've only really scratched the surface so far. Yeah.
I don't get this wrong. So we now know that we have more switchbacks near the sun, and you try to explain that this might be responsible for solar wind acceleration. Is there any paper or something like trying to utilize this?
Yeah. So let me explain try to. So the straight answer is there's tons of papers. Theoreticians jump on things really quickly. So there's a paper that just came out from Alfred Mallet. There's a whole tradition. There's a story of Alfvén waves accelerating solar wind. I didn't want to get into the details. I'll talk about that tomorrow because I didn't explain what an Alfvén wave really is. So, but assuming that you accept the fact that these waves can push the wind, these are really just large amplitude Alfvén waves. Okay, and so there's many different effects that happen. One of them, of course, is that the amplitude changes with distance from the sun, and that has to do with, it's not really the conservation of energy, because in a flowing medium, energy flux is not conserved, but it's called wave action conservation, if you like. There's an invariant, which is the equivalent of energy when a system is time dependent. It's called the action. You all know it from mechanics, right? If you have a pendulum that's oscillating and you start moving the vertex of the pendulum, the energy of the pendulum is no longer conserved, right? But what is conserved is the ratio of the energy to the frequency with which you're oscillate with to the frequency. That remains conserved as long as the rate at which you oscillate the vertex is slow compared to the period of the pendulum. And the same cases for the solar wind. As long as the alpha waves have a frequency which is higher than the typical transit time or the typical length scale over which the solar wind accelerates, then the wave action is conserved. Why is it wave action? Because the waves push the wind, and so they lose energy to the solar wind as they move out. Okay, so the amplitude changes. At the beginning, it grows because the dominant effect is the density fall, so the amplitude grows. And then the dominant effect becomes the fact that they're pushing the wind, and so the amplitude goes down again. And so there's a peak in the fluctuations that you can calculate, not very difficult. Now, that's done for standard transverse waves, but a theory for spherically polarized waves doesn't exist. Okay, so there are many papers that talk about little pieces. How do I get spherical polarization? What does it imply for the relative amplitude delta B over B? Does this amplitude change explain the formation of switchbacks? How do I get from a shock being formed to the spherical polarization? There's tons of papers discuss all this. But the simple question, apparently simple question, how do the spherically polarized waves accelerate the solar wind? Has not been done, not properly yet.
So we've got a whole load of data from Parker Solar Probe and more coming back from Solar Orbiter at the moment. Would it be that kind of spherically polarized waves is the next thing that you would want potentially a new mission to look at? What's the kind of next step, and do we have a mission that's going to address that yet, ignoring politics? Is that something that's being proposed at the moment?
I think if you're asking a more general question is what would drive the science of a new mission. This is then a personal opinion. Okay. My personal opinion that there are two things that we really need to do. One is to go even further in, because remote sensing gives you a lot. And I think there's a lot we can learn with new techniques from the accumulated remote sensing data that we have. But there's intrinsic value in situ. I mean, if you could give me a chromospheric return mission, I'm just making a joke here. I'm not saying that we go scoop up a piece of chromosphere and bring it back. But if we could get in, as close as we can, that'd be something to do. And the other thing is that we really need to nail the dynamo problem. I mean, this is in some sense, it's exasperating, and it's exasperatingly difficult because we need to go to high latitudes and we need to measure for a long time. So one of the people at our table today was discussing the fact that maybe AI and these techniques can be used to bring data from different missions, cross-calibrate them properly so that you can produce long time series from intrinsically shorter time series. That would be, I think, tremendously useful for the dynamo. But for a spacefaring society like we like to think of ourselves as becoming, I think we need to put a series of telescopes in the heliosphere such that we get 3D measurements of the heliosphere. We need a polar, we need a systematic. If you ask me, we need at least 2 satellites that go, antiphase above and below, and then a string of satellites around in the ecliptic so that you can get a 3D measurement of the magnetic field of the sun. I think that would cause a major advance in our understanding of CMEs and intermittent behavior as well, but it probably would lead to significant progress in understanding of the way the magnetic field opens up. I didn't really talk about the magnetic cage and the fact that the opening up of the magnetic field is a fundamental issue. And it's related to the confinement of plasma and fusion machines, of course. It's kind of the same problem turned upside down. Vika, do you want to add to something like that? I don't see why not. Okay. I think Parker has shown, from the point of view of just basic solar wind physics, I think two fundamental important discoveries. One is that alphanic fluctuations play a major role in solar wind acceleration, period. For all solar wind types, except perhaps in the neighborhood of the heliospheric current sheet. I mean, which means in the neighborhood of regions where these poor waves can't propagate, poor things. Because if the field vanishes or turns around, the waves don't propagate. So I think that's one. And two, understanding of turbulence, how turbulence develops and evolves in the inner heliosphere. But now if you ask me, what's the source of the alpha waves? I think we have some insights from Parker, but we don't have a solution. So there's some fundamental coronal physics that we still are lacking. That's one. And I think for solar activity in particular, I think we've learned a lot about the local acceleration of particles at shocks and reconnection sites from Parker. We are still missing some very important information there as well. So again, I think I'll repeat the answer that I gave. I think we need to go closer and 3D. So I really think, I don't know whether one nation can afford to create this kind of multi-satellite 3D measurement. But I think that's going to become essential if you want to have any chance. I mean, I think I'm going to say something that might be very unpopular. CME generation and acceleration has been stagnant, I think, for many years. Okay. And the reason is that we suffer from confirmation bias, strongly so in this particular field. And I'll give you a very simple example. When people in codes make CMEs, they literally make CMEs. What do I mean by that? They put the CME in the solution at the beginning. They take a field, they plug a flux rope that they know is going to become unstable into that system. And then, of course, they let it go. And hey, it becomes unstable. That's not what the sun does. The sun produces something that's in equilibrium beforehand. And there are very few simulations that do an ab initio calculation without lugging in a flux rope, that take the surface evolution of the field and try to evolve that without any additional information and get something like a CME coming out. And I think this is caused, it may be helpful, because once a CME is initiated, you want to understand how fast it will get to Earth or things like that. It's helpful for that. But if you're trying to find out how a CME forms, you're kind of cheating, right? And if we continue cheating that way, I don't think we're ever going to understand the details of how it forms.
Could you repeat the explanation for why current sheets become unstable?
Can I reverse the question and say, why would you suspect that current sheets are stable? Let me turn it around. The reason I'm saying that is quite simple. The plasma is a continuous medium. If currents start flowing someplace, would you expect it to be in equilibrium? Current sheets want to thin. They technically want to become infinitesimal, if they can. So something has to intervene to stop them from doing that. It has to be either the magnetic field configuration with a normal component, like in the tail of the Earth, or some pressure system. Something has to stop them from doing what they want to do. And it's that something that stops them that sometimes is effective, but more often than not, even a small perturbation makes it effective. So I would turn it the other way around. I'll talk about this more tomorrow. We'll study the beginning of reconnection, and I'll explain why even though Sirovatsky had understood perfectly well that this was the case, it took so long to get to an answer to that question.